In this tutorial, we will learn how to do a hierarchical linear regression. And so when we do a hierarchical linear regression, this is simply an extension of multiple linear regression, except that we're comparing different models and specifically a nested model. Okay, so let's take a look and see what we have in store for today. So make sure that you have RStudio open. Let's go to File, New File, RScript. Open up your script editor window here. This is where you're going to save your RScript file. And then let's do a hashtag to make an annotation. And note that this is hierarchical linear regression, or HLR for short. So just to preface this, you are going to be running multiple linear regression models with hierarchical linear regression. What matters is that we are just adding on model comparison tests here and looking at things like the change in R squared, or in other words, the change in variance explained from one model to the next, where one model has a subset of the variables, the predictor variables that the full or the final model has. Now, because we are doing multiple linear regression at heart here, all the statistical assumptions that should be satisfied or met need to be met when you're running hierarchical linear regression. Now, for the purposes of this tutorial, to keep things on the briefer side, I will not go into statistical assumption testing for these data here, but if you are applying hierarchical linear regression to your own data, and there are true consequences at stake, then definitely check out the tutorial on multiple linear regression and do a review on which statistical assumption tests and which statistical assumptions need to be met and which types of diagnostic tools we can use for that. All right, so with that said, let's jump into this tutorial. So the first thing we need to do is set our working directory. And my working directory, I'm going to set it using the setwd function. And in quotation marks, it's my H drive R workshop folder here. Yours will likely be different. I'll click run. You can see down here blue. Now we've set it that our working directory is set. Now this is the folder that I've set where the data file we're going to be working with today has been saved, or rather I've saved it there. Now alternatively, you could set your working directory by going to Session, Set Working Directory, and Choose Directory if you choose to do it through drop-down menus. So the next step is to read in the data. And so the data file we're going to be accessing today that's saved in the working directory folder is called paydeterminants.csv. It's a comma-separated values file, hence the .csv. And so if you haven't recently done this or you've never done this, make sure that you've installed the reader package, because we're going to use the read_CSV function from the reader package to read in our data as a data frame. So I've recently done this, so to save time, I'm not going to do the install for the reader package here, but I am going to use the library function, which everybody will need to do. And as the sole parenthetical argument there, enter the name of the reader package there, which is READR, all lowercase. And let's run that line of script there. We get the blue text down here in our console. Everything seems to be all good. And now let's come up with a name for our data frame object that we're about to read in using that read_CSV function from the reader package. Well, let's call it PD. That's a lowercase p and d for pay determinants. And I'll use a left-handed arrow to assign the data frame to this object. And so we'll use that read_CSV function I've been alluding to. And as the sole parenthetical argument in the quotation marks, the name of the data file is pay with a capital P, and then determinants with a capital D.csv. So don't forget the .csv extension, because this is a .csv file and a .csv function that we're using. So let's click run there. Okay, so as you can see, it was a success. We've read in our data frame object that we've named PD. Let's take a look at it and orient ourselves to the data we have access to. So our dependent variable, or outcome variable of interest, is going to be raise. And this is the percentage pay raise that each employee received here. Now, this is going to, again, be our outcome of interest here. Our predictor variables are as follows. We have the education level of each employee. So where education is numerically coded, it's an ordinal variable in terms of measurement scale, but it's numerically coded such that 1 equals, let's say, a high school diploma or high school degree or a GED. A 2 is some college. Let's say 3 is an associate's degree. A 4 is a bachelor's degree. And 5 is graduate school or professional school of some kind. Now, the variable here stands for performance rating. This is supervisor rating of performance. And then we have two protected class variables here, which are sex, which has the categories or levels of male and female in this data set here, this data frame. And then we have race, which is also a protected class variable, which has the levels of Asian, Black, and white here as the three levels or categories as they're sometimes called here. And so what we're going to be doing is a two-step hierarchical linear regression model process. And in the first step, we're simply going to see, as you would expect, you'd probably expect that someone's education level and performance level is going to influence their raise. You would expect that that would be probably consistent with the organization's pay policies and practices. Now, what you'd be more concerned about is if you started seeing, let's say, the sex of an employee or the race of an employee or both influencing how much of a raise they get in terms of percentage raise. So in the second step, we are going to add the sex and predictor variables to our model. And then we'll compare how much additional variance explained, if any, is explained by sex and race when controlling for the variables that were already in the first step, which is education performance. Okay, so let's get to it. So you typically in hierarchical linear regression, we call each phase or each model as being a step or a block. And so you might hear either of those either bits of that language used. And so this first block we're building is actually going to be a nested model here. And in that its variables will be a subset of a more full model that will come in a subsequent step or block. Okay, so for the first step, and I should note here that I'm going to be using the LM function. So that's LM for linear modeling in this tutorial because it's a bit more flexible. I find it easier to use when you're comparing nested models and so forth. If you're just running each model separately, you can by all means use the regression function from lessR or the short version of it, which is regbrief from lessR. But if you want to get comfortable with using the linear modeling function, it's a really nice function. It's very flexible. It's easy to assign it to an object that then you can reference in other functions, and not as easy to do that with the lessR regression functions. The lessR regression functions are fantastic for doing single model analyses, but if you want to start comparing models, you might consider using the LM function. Okay, so for this first step, let's create a first model that we are going to call, let's name it step 1. Use the left-handed arrow here to assign this model that we're going to estimate to this object called step 1. And we'll use the LM function here, so linear modeling. And the arguments will be the same as what we would do in other regression functions, such as the regression or regbrief functions from lessR package. So if you recall, our outcome variable is going to be raise. And in this first step, the predictor variables will be education and perf. So edu and perf. Okay, so raise is going to go to the left of our tilde. So this is the tilde symbol here. So the outcome variable comes to the left of it. And then our predictor variables of education, so EDUC, all lowercase, plus if we want to add additional predictor variables, so this will become a multiple linear regression model now because we have 2 or more predictor variables in the model. Our second predictor variable is performance, or perf for short here. Okay, so we've specified our regression model in this first step here. The second step is going to be to do data equals and the name of the data frame from which these variables come from, which is PD. That's what we read in, and that's what we've named the data frame. So PD comes next here. Let's run that line there. And so you'll see that you don't get any output because we haven't actually called for a summary of this model yet. And so before we do that, one thing that this model summary that we won't get from the summary function that we'll use in a moment is we don't get the sample size, the effective sample size after, in other words, the number of cases that were retained after any missing values missing values were deleted and by association cases were dropped or removed. Okay, because if we look at the original data frame here, we see there's 132 unique cases. But, and we don't in this situation have any missing data here, but let's just run this in case we had. Okay, so this is going to actually be nested models here, or nested functions rather here. And so what we're going to do is in row, so we're going to call for the number of rows in an object. And then we're going to put another function as the argument here, which is model.frame. Okay. And then we are going to put the name of that model object as the sole parenthetical argument within the model frame object, and that model, or the model frame function, and that model frame function comes within the in-row function here. Okay, so let's click run there. Okay, and so you'll see in your console you get 132, so that's how many people were retained for analysis in this model. Now, what if we want to get the actual regression coefficients and the model summary information from our regression model called step 1? Well, then you use the summary function from base R here. Okay, so both the LM function, the in-row function, model.frame function, the summary function are from base R, so you don't need any special pack or additional packages you need to install. These come standard with R here. So in the summary function, type in the exact name of that object we created up here, which is step 1. And you can click run to take a look at the output here. Okay, so we get our typical regression information here. Let's drop down to the coefficients for our model first. And so you interpret this like you would with any multiple linear regression model. Okay, so here we have the two predictor variables, edu and perf. And you can see that if we look at their regression coefficients, they're both positive. These are unstandardized. And the p-values are both less than the conventional two-tailed cutoff of 0.05. And so we would conclude that both education and performance are statistically significant predictors of the percentage pay increase that someone receives. Okay? And so the way, if you wanted to interpret this, for instance, with performance, for every 1 point increase in performance, the percentage raise increase that someone would receive is about 0.296 or so. Okay? And again, both these are statistically significant. And when we interpret each of these, we would say when controlling for the other predictor or predictors in the model, just like we would with multiple linear regression. Okay, so here we have a model. Both predictors are statistically significant. Now, when we're talking about hierarchical linear regression, we also tend to focus quite a bit on the model fit information, specifically R squared. And so let's take a look at our unadjusted R squared here, which is listed as multiple R squared. And you can see that for the model, it is 0.384, let's say. So what that indicates that in this sample, these predictor variables explain about 38.4% of the variance or variability in the percentage pay raise that someone receives. Now we also have the adjusted R squared value here, which is 0.374. So a little bit lower as it is because it's adjusted for sample size and the number of predictors in our model. The adjusted R squared tends to be a better estimate and more accurate estimate of how well these factors or variables explain variability in the outcome in the underlying population. So not specific to the sample, but this is more broadly to the population from which that sample is drawn. Okay? All right, and then you have the F statistic, otherwise called the F value. And this indicates the value itself doesn't have a lot of meaning. Here you have 40.16, it's degrees of freedom. But what we're really interested in here is the p-value. And so what this p-value tells us is that this model with these two predictor variables fits the data better than a model without these two predictor variables here. So that's not a super high bar to begin with, because we're just comparing a null model with no predictors and the same outcome variable to a model here where we do have two predictor variables in this case and the same outcome variable. Okay, but this becomes consequential when we'll look at the R squared change here in a little bit. Okay, all right, so that is the first step of the model. For the second step or block, let's do block 2 here, step 2. We are going to do essentially the same thing. So let's copy what we did above there. Okay, and so now we're going to we have our second step. So let's name the second model step 2. And then we'll keep the same two predictor variables, education, performance, as we did before. But now we're going to add sex and race. Remember, these are case and space sensitive, so they need to be the exact same variable labels as we see there. So now we have a fuller model here, and you can see how this first model, the step 1 model, is nested within this bigger model that also includes sex and race here, okay? And then we're gonna come down here to this script for in-row model.frame, and instead of step 1, we'll change that to step 2. And the same goes for the summary function. We'll just tweak that to step 2 from step 1. All right, so let's go ahead and run our model, okay? Let's see what our effective sample size is. Still 132. Apparently no missing data there. And then let's do summary of the step 2 multiple linear regression model we just ran. Okay, so now let's take a peek at this model. And what you'll see is that both education performance remains statistically significant when controlling for the other predictors in the model. And you'll see that sex in this case is not a significant predictor of the percentage pay raise someone received, because the p-value is equal to or greater than 0.05 when controlling for the other predictors in the model. Now, for race, however, we will see that it is a significant predictor of pay raise in percentage increase when controlling for all the other predictors in the model. And so what you might be wondering, why do we have 2 different regression coefficients associated with a single variable? Well, why this is happening is that this has been dummy coded, which is the actual name for this, sometimes called contrast coding. And so what's happening behind the scenes, so it's really nice about this function, this linear modeling function, the LM function from base R, is that it automatically, for character type variables, it automatically will create a dummy variables behind the scene. And so it's a little bit too, I don't want to get too much into it in this tutorial to keep the length down, but if you check out the written tutorial, I go into more depth about dummy coding and what it means. So for this tutorial, I'll just explain how you interpret it here, okay? So what is happening is that this first entry here, which is race black, and then race white is the second one. Remember, we have 3 different levels here. We have Asian, black, and white for the race variable. Those are the 3 levels or categories. What this is saying is that when you compare black employees to Asian employees, and you might be saying, why Asian employees? How did you know that? Well, it's going to treat when you dummy code, you're going to treat one of the levels of the categorical variable as a reference group. And the default is going to be, if it's character data, to treat the one that is first alphabetically as the reference group. Asian begins with an A becomes before B for black and W for white. So therefore it's the reference group, okay? And so actually the mean value on the outcome of percentage raise gets reflected in the interceptor constant in the model, controlling for other variables in the model. Now, if you check out the written tutorial, I do a demonstration in which I show how essentially this is equivalent, or it is equivalent to a one-way analysis of variance. And I show what would happen if you removed the other predictors from the model and just ran the race variable by itself in relation to the raise outcome variable. And I'll show the equivalence between how these really are just mean difference estimates here. But what you can interpret this as in this model is that this means a positive value here that is statistically significant for this regression coefficient. So this positive value of 0.587 that is statistically significant indicates that black employees receive higher percentage raise than Asian employees. And then we come down to white here. For race, we see also a positive regression coefficient, and this one's larger. And we see that the p-value is also less than 0.05. So this is also statistically significant regression coefficient, meaning it's statistically significantly different from 0, or that's how we're treating it here. And because this is positive, it means that white employees have a significantly higher pay raise percentage increase than Asian employees in this data set here, okay? So that's how you interpret this here. So we do see some race effects here, which this would be in a real context, or even in this imaginary context here, this is going to be pretty concerning. Essentially what this is saying is, even after you control for education, performance level, that the race of the employees is still affecting how much of a percentage increase they get in raise. Well, that's obviously going to be concerning there, and may be evidence of either implicit or explicit bias, or both, and potentially some type of discriminatory practice, or at the very least practices that are resulting in adverse impact in some way against people of certain protected classes. Okay, so that's one part of our interpretation here, and this would be the same for any multiple linear regression model. But then we come down to the model fit information here, and we see that the multiple R squared, which is just the unadjusted R squared, is 0.5923. So here we see the variance explained increases from our previous model is 0.3837 when we just had education performance in the model. But when we add race and the sex of the employees, it increases by about over 20% here. So about 59.2% of the variability in the percentage raise someone receives can be explained by their education level, their performance level, their sex, and their race. Okay, and then we have here the adjusted R-squared value, which is slightly lower as always, and it's 0.576. And then we have the F statistic, which here and its associated p-value is less than 0.05. And so this indicates that this model with these predictor variables, these 4 predictor variables of education, performance, sex, and race, fits the data significantly better than a null model without any predictor variables. Okay, so now we're ready to do some actual nested model comparisons here. Or in this case, it's just a single comparison. So we're going to compare the nested model with the full model here. And so how do we do that? Well, we're going to use another function from base R. It's called ANOVA. Okay, so it's ANOVA all lowercase. And what we do is we simply take the first model name, which was step 1, if you recall, this comma. The second argument is going to be a second model name, which was step 2. So here's the hierarchical part here. And we're going to see if the second model fits the data significantly better than the first model. And so you can start to imagine that this is a more stringent test of the typical, which is comparing our model fit of the focal model to a model with no predictor variables. Now we're saying we're comparing a model with all the predictor variables, in this case, to a model with just some of the predictor variables, and whether it fits the data specifically, or it fits the data significantly better here. Okay, so let's go ahead and run that. And so you'll see it reminds you what each model is here that you're comparing. And so we should know that already. And then what we're ultimately interested in here is the F value and the P value here associated with it. So this P value is less than 0.05, which is again our conventional two-tailed cutoff for statistical significance. And so what this indicates is that the second model here, the fuller model or the model with more predictor variables, fits the data significantly better to a statistically significant extent than the model with just some of the variables. So this is our nested model here, the first one, which is step 1 or model 1 as it's called by default here. And this is our full model in this case, which has the same variables as what was the nested model plus the sex and race variables. Okay, so we know there's a statistically significant difference, but how big of a difference are we talking about here? Well, to do that, let's actually calculate the change in R squared, okay? So the change in R squared is fairly straightforward. We're going to use some basic arithmetic here. And so to calculate this, we are going to use the summary function again, reference the second model, because we're going to take the second model's R squared value minus the first model's R squared value, okay? And so put step 2, summary, step 2, and then $sign. And then we're going to reference from this summary object our summary function, we're going to reference the R squared coefficient or information that's going to be, that comes with that model. So we're going to actually pull it out. So we use the $sign to pull that value out. And actually, if you were to just run this by itself, you would see, oh, there's that R squared value that we just saw up here of 0.5923, which is for the unadjusted R squared value, okay? And then the second thing we're going to do, let's copy this first part so we can adapt it. So we're doing the R squared for step 2, and then subtracting from it the R squared for step 1. So let's paste this here, change the step 2 to a step 1, and everything should be good. Let's click run here. Okay, so here is the change in R squared here. In other words, the difference in R squared. So this is sometimes referred to as delta R squared, where delta is represented with the Greek letter of delta, which looks like the triangle, or is a triangle. And so that would indicate change here. And so this is exactly what we did mental math with a little bit ago, where we said, hey, I think that the difference between this for the first model, step 1, 0.383 or 0.384, and 0.5923 for the second model or the second step is about over 20%. And here we see that reflected here of 0.208. So in other words, about, well, let's round here, well, almost 21% increase in R squared, or the amount of variance explained by the second model relative to the other model. So that's a pretty concerning amount given the context here. And so if you recall, what are our rules of thumb for R squared if we're trying to interpret the magnitude in this specific context, which is more consistent with the general context for interpreting R squared? Well, let's say I'll do R squared rules of thumb here. And so for it to be small, let's say it's going to be approximately a 0.01 R squared. And for it to be medium, it's going to be about a 0.09 R squared. And for a large, it's going to be about 0.25. Okay, so we're talking somewhere between medium and large here. And again, the context here is pretty powerful, that we're talking about knowing the race and the sex of the employees and adding that to our model explains over 20%, nearly 21% more variance in the percentage raise that someone that receives beyond that of education and performance level that they demonstrated. So again, this is going to be concerning here. And so sometimes we call this change in R squared here, we call this incremental variance explained. So I'll put that as a little note here, incremental variance explained. And so you can think of this as being, instead of a typical regression model, or if we're looking at one model by itself, we're just focusing on, okay, education is statistically significant, or it significantly predicts percentage raise someone receives based on the model results here, controlling for everything else in the model. You can think about, when we're doing nested model comparisons like this, we're actually almost thinking of the controlling at the model level. So we're controlling for the predictors in one model and seeing if the predictors we added in the second model, which is step 2 in this case, explains significantly more variability, and to a statistically significant extent. All right, so that is how you can do hierarchical linear regression, which again involves nested model comparison. This can be a pretty powerful tool, especially when you want to look at steps or blocks of predictor variables. Now, in terms of the logic behind this, we could have, it depends, in terms of what order you're going to do variables, it really depends on your research question. Here I wanted to control for education performance level and then see if sex or race explained anything above that, and it did. Alternatively, in other contexts, you might have a reason to actually put the protected class variables or other control variables as first, and then see if your focal variables explain significant variability in the outcome above and beyond those control variables that you have, or those that you've designated as formal controls or covariates. All right, so this wraps up the tutorial on hierarchical linear regression in R.